Greetings, in this video let's talk about what it means when something is an open set and a closed set. This will be in the context of topology, namely we need a topological space to consider one. So the definition of a topological space, by the way, had been covered in a previous video, so if you don't know, rather watch that first. It's a particular previous video on this channel, so you can go and watch that if you want. Let's consider underlying set X and topology tau on it. Now let's talk about a particular set that I will choose. Let's say that I set X equal to these three elements that are contained in it. And then now let's contain topology as a collection of subsets of X that satisfy certain properties that had been mentioned in the definition of topology and topological space. So of course every topology has to contain the entire set and then the empty set and then some more subsets. At least these two, if only these two are contained, that could be sufficient topology. A trivial one, but let's talk about one that's a little more complex, contains also some other subsets, adding to the probability that it won't be valid, but we will make sure that we will check and make sure that it is a valid topology. So let's say there's this element 1 containing it, then there's 2, and then there's going to be 1, 2 inside. Now, yeah, this should work as a valid topology, because we have these two that must be contained, and then any union of these elements has to be also contained in tau. Well, union of these two is this, union of anything else makes sense and will be either this, or the entire set, or yeah, and finite intersections of some of these elements. Well, this and this has nothing in common, this and this has the 2 in common, this and this has the 1 in common, this and this has nothing in common again. So that works out. This topology is a valid one. And now to talk about open and closed sets. So open sets, I can write it right here. Open sets, what that means is they're member of tau. So on a particular topological space, we talk about open sets as basically simply the members of tau. What are the members of the collection of subsets of X? These subsets, these sets here, are open sets. Then closed are their closed sets are the complements of the open sets. So just look at whatever the members of tau are, take their complements inside X, and those sets are closed. So complement of X of the whole set is empty set. Complement of the empty set inside X is the whole set X. Then the complement of 1 in X is the remaining 2, that's 2 free. Complement of 2 is 1 free. Complement of 1, 2 is free. Alright, just to check it, complement of this in X is 2 free, this is 1 free, and this is 1, 2. Alright. So now that we have this, a complement of this is 3. A complement of this is 1, 3. Alright. So now that we have this, another term can be introduced, which is also often used, and it's namely, this was 2. It's namely clopen. Clopen means that a particular set is both closed and open. It can happen because these are not opposite. As in usual language, they are basically, what it means is there's a definition for what open is, for what closed is. If a particular set satisfies both, then it is clopen. We see that clopen are the empty and X here. And then the other clopen, well, we don't really see any other clopen here because this one has no same set member in the closed, among the closed ones, this one also. So we see that in this particular set, and it very often happens, the only clopen ones are the trivial elements of tau. There's no other clopen sets in tau. So this is the definition of closed and open sets. There's many examples to take it into account. One can learn far more by looking at those examples, checking out. There's many examples in which there's actually clopen sets also. They are not just the empty and X. There's more clopen sets in other topological spaces with differently defined, let's say the underlying set and topology, but that's up to what example one looks at.